Welcome to this lesson on the beginner's guide to performing multiple linear regression in Python using Scikit-Learn. Today we're going to cover what multiple linear regression is, how to perform EDA on the data to determine procedures and data quality for linear regression, learn how to numerically encode categorical features, perform linear regression with multiple features, evaluate the performance of the model, and interpret the results. This multiple linear regression is an extension of the simple linear regression where we had only one independent variable to predict our outcome. For multiple linear regression, we have multiple independent variables to predict our output or our outcome, and we do that by using the following equation. Here, y is the dependent variable, and the x's are the independent variables or predictors. Beta sub 0 is the intercept or a constant term. If everything else was 0, what would you have left? This is the constant. The beta 0, beta 1, and beta 2 are those are the coefficients, and we'll call those the parameters for the model. The whole focus and purpose or the goal of multiple regression is to estimate these parameters or these beta values. And we want to estimate them so that when we have the equation and we get our output, our predicted output, that predicted output is very good and very close to the actual output. So we want to minimize the sum of the squared differences between what we actually have or our observed values and the predicted values that we get from the equation. Mathematically, the objective function or our sum of squared differences function is also known as the loss function or the cost function, and is given by the following equation. What this equation is, what it's saying is that for every value of y, the actual value of y, we're going to subtract the predicted value. So when we see all this information here, this beta 0, beta 1, all this here, this is the predicted. This is from the equation. This is the y from the equation. And this yi represents the actual value. So our actual value minus our prediction, our predicted y, squared. We want to minimize this. Here n is the number of observations. So if you have 100 records in your data set, or 100 rows, or 100 observations, then you would have from 1 to 100. And each one of these is representing one row or one observation. So here, this might be observation 1, observation 2, and these will change. These will update. The methods for finding the best coefficients. Well, the way we're going to actually find these coefficients, we're going to let the computer do the heavy lifting on that part. But what's actually happening under the hood is we're using calculus to basically set the derivatives equal to 0, okay, and we'll solve the resulting system of equations for each beta value. And so this can be done using various methods such as the normal equation, gradient descent, or matrix factorization techniques. I would encourage you to check out Khan Academy's lesson on gradient descent. I think I'll create a video in the future also on gradient descent, and we can talk about that some more then. In this lesson, we're going to cover multiple linear regression to predict medical insurance costs based on several features. As I mentioned before, some of these features are going to be non-numeric categorical features. For linear regression, we have to have our categories in numeric form, and we can do several different techniques for converting your categories into numbers, and today what we're going to use is one-hot encoding. Okay, so here we are in Google Colab. I like using Google Colab. The version controls that you have to do between the packages is pretty much handled here, very much like it is with Anaconda. The benefit being, though, that you don't have to download a Python or Anaconda if you don't have the space on your machine. Today we're going to work with the medical insurance cost data set that I found on Kaggle. I'll add this to our GitHub so you can have access to this, and also the code that we're going to use to create our model today. Alright, so let's get started. We're going to import the same libraries that we had last time, pandas for data frame manipulation, NumPy also for handling arrays, and Seaborn for visualization. And we have from Scikit-Learn dot model selection. This is another reason why I like Google Colab, is that it has the autocomplete feature. We're going to import our train test split. And since I'm going to be using from Scikit-Learn dot a lot and import, what I'm going to do is copy this a few times because I have a couple of others that we're going to add. So from Scikit-Learn dot linear model, I want to import the linear regression. And we need to be able to determine how good the model fit is. So just like we did in the previous video, we're going to import the metrics, and the metrics that we're going to use are the R squared, our 2 score, and also our mean squared error. Some new packages that we're going to include today will be for converting the categorical columns into numbers, and we're going to use that with our pre-processing. So from Scikit-Learn dot pre-processing, we're going to import one hot encoder. And finally, we're going to also import column transformer from the compose library. So here we have column transformer. And what column transformer does is it allows operations to happen on individual columns simultaneously to curate a data set. So we're going to see how that actually works. Let's go ahead and run these. All right. And read in our data frame. pd.read _ CSV. I'm going to copy the path of the file and Control V. And let's also take a look at the first 5 rows of the data frame. Sometimes I'll use df.sample so we can get a sample of the different rows, but here I'm just going to take the first 5. These are our features in our columns. Charges is our target or ground truth or our output feature or variable. Here, let's take a look at what this row represents or what it means. Here we have age 19, so you have someone that's 19 years old. She's female. Her BMI is 27.9. She has no children. She's a smoker from the Southwest. And her charges, medical charges, are $16,884.92. Let's take a look at how complete the data set is to see if we have any missing values. I'll do with df.info to get some information about the data set. And what it shows us is that we have 2772 or 2,772 rows or records. And we notice that for each one of the columns that there are no missing values. Okay. So it's no missingness, which is great. I also like to look at the data type to make sure that that is coded correctly, because if it's not, we'll have to recode or change the data type basically. So here's the age, it's integer 64, sex should be an object, which is a category, BMI is float or a decimal form, children is integer, which is correct, smoker and region, those are also categories, and charges is what our target feature is, and it's a decimal, so that's our medical charges. I would also like to take a look at the summaries of the numeric features. This is basically what you see in a box plot, or is sometimes references to 5-number summary. So let's go df.describe. Okay, and so here we see for age. The reason why, and let's back up just a little bit. The reason why I like looking at the describe is that it lets us know if we have outliers, and we'll do two things: look at the describe and also look at an image or a graph of the data to see if we have outliers. Outliers can be very can give you bad results for regression, linear regression. So it's important to kind of look at those and treat them as necessary. So for age, what I'm looking for is, how it compares with the mean and the middle or the 50th percentile. If they're close, we're like, okay, that's pretty good. Look, also looking at the minimum and the maximum values to see if there are any extreme values there, but they seem to be on target for age. So here for age, we see that the average age is 39, that the youngest age or youngest person is 18, and with the max of 64. So we're seeing 39 for the average, 39 for the 50th percentile, which is close. The BMI, average BMI is 30, almost 31, 50th percentile 30. The max BMI is 53, with the minimum BMI being about 16. And so here, that's what are we seeing for standard deviation? About 6. Okay, 6 units. For the number of children, average number of children is 1, and also 1 for 50th percentile. Max is 5. For charges, we do see more spread in charges, with the smallest amount being $1,100 in charges, $1,121, and almost $1,122, and the max of $63,770. So that's what we see down here. All right, so now that we've taken this look, I don't see anything that's like very, very large with regards to being extreme outliers, but let's also take a look at those correlations between these features. Correlations let you know if there's a strong linear relationship, either positive or negative, and so let's look at that. To get our correlations, what we want to do is I'm going to make sure that I want to get the correlations for these features here: the age, BMI, children, and charges, and not the categorical features. So let's try first with df.core for our correlations, and you'll notice that we could not convert string to float female, so it's trying to do correlations on our categorical features as well. So what we're going to do is, I'm going to show you what we're going to do first. We're going to select data types. So df.select _ dtypes, and data type we want to exclude. We want to exclude those that are object data type. So I can let you see what this looks like. Let's take just the head of this to let you know this is actually a way to subset our data frame. So here, if you look at it, see now what you see is just age, BMI, children, charges without the categorical columns. So we're going to take this same df.select object, exclude our object, and we're going to take the correlation for that because we want to see what the strength of the relationships are, linear relationships are for each of the numeric features. What we want to see if there's like anything that's like close to 1 or -1, as we mentioned before in our previous video. And so here for age, I'm not seeing anything very strong. I think what we want to of course focus on as before is our output feature, which is charges, and how it compares with the other features. So we have charges compared to age, and we end up with 0.29. So it is a positive correlation between age and charges, which means that when age goes up, charges goes up, and it's not a very strong relationship because it's not close to 1 at all. So it's below 0.5 actually. The children, the slight positive correlation. BMI also slight positive correlation for increase in charges. We don't see very strong correlation between the other features, which is good. That means we're not likely to have multilinearity in this data set. Because the correlations are so low, You might think that we could potentially use a different equation for predicting medical charges for a different algorithm. Okay, so let's take a look now. We're going to use our Seaborn here, SNS dot pair plot, and also do a visual inspection of these numeric features. Again, we're using our df.select d types for this. Okay, and as you can see, again, with charges compared to age, BMI, and children, we see again with age that there is some sort of slight trend, and as age increases, we're seeing an upward trend in charges. BMI, you can still also see that with the increase in BMI that we are seeing some increase. Not a strong increase, not really for either of these, but we saw that with the correlation coefficients. Let's take a look at our categorical features. We're going to use the same D types, except now we want to include the category. So instead of exclude, we're going to go include. And what that include does is it provides us a data frame just with these categorical features. Let's just take a look at it real quick so you can see. I'm just going to look at the first 5 rows of that so you can actually see what that is. So see, now we're just looking at this. Okay, just the categories. So we want to list these categorical features. And I honestly want to list the categorical feature columns. I want the columns. So I'm going to call this categorical features. This is going to be equal to this. I don't want the data frame, I want the columns. And I want to put those columns in a list. Okay, so we get sex, smoker, region. So just are basically our column names. One thing that's important to take a look at when you have categories like this is the subcategory. If you have, or sometimes I refer to it as a level of the category. If you have a lot of levels or subcategories, when modeling, sometimes it's best if possible to group those or regroup them so that it's easy to interpret the model results. So here we're going to take our categorical features. So for category or for column in categorical features, we are going to print the column name, and we'll print what the levels are or what the subcategories are for each main category. So df call dot unique. Okay. And so here we have for the sex category, our subcategories are female, male, smoker, yes, no, region, southwest, southeast, northwest, northeast. Okay, so we're going to one-hot encode these. We're going to convert these into separate columns. So instead of sex as one column, we'll have sex female, sex male. Those will be 2 columns. And underneath sex female, if the person's female, you have a 1. If the person underneath the sex female column, if the person is male, there will be a 0, and the same for male. So what happens here is that you end up with duplicate information. And for linear regression, we don't want to have this duplication because it introduces multilinearity, which can be problematic for model results. So what we will do is we will drop one of the columns. We'll use a drop first with the one-hot encoding, and we'll see what that looks like. But first, let's go ahead and separate the features in the target variable. So we have x is equal to df.dropCharges, and we're going to drop our charges. We're going to drop our charges from the column. Okay, so this is a column that we're trying to drop. So x is equal to 1 for column. If you're trying to drop or perform the operation on rows, you would have x is equal to 0. So here y is equal to df charges, and we're going to perform our one-hot encoder. We're going to call this one-hot encoder is equal to 1 hot. So we're going to drop is equal to first. We're going to create a transformer, and our transformer is going to be column transformer. And for the column transformer, we're going to append each of the new columns with the word 1 hot. And for those, we want to tell them that we're also going to make sure that we have our 1 hot encoder included. So we have 1 hot. So this is what we're going to actually do to the columns. So 1 hot encoder. And what columns are we talking about? We're talking about our categorical features. So here, this is our categorical features. And the column transformer is going to allow us to be able to perform multiple operations on the different columns and also keep the remaining columns that we have. And so this is our remainder, and remainder is going to be equal to pass through. And pass through is going to allow us to keep our numeric columns without any operations happening on them. If you don't have the pass through, you can also drop them, and then you won't have those numeric columns. But I want to create a data set that has our transformed categorical columns along with our untouched numeric columns. So we have X encoded, and that's going to be equal to our transformer. I have it right. Transformer fit. Our transformer dot fit underscore transform, and we're going to transform X with this 1 hot encoding and transformer. Did I miss something? I think I did. Oh, that's my problem right here. My bad, you guys. Alright, so I'm going to have to fix this one. I'm going to do this one. Okay. Now, we're going to take our transformed features and get the name. So we're going to say transformer dot get the feature names out. And the reason why we're going to want to do this is that I want to create a data frame so you can see what's actually happening under the hood with regards to the new data frame that we're going to be operating off of, or the data that we'll be operating off of now after the column transformer and the 1 hot encoder. So let's take a look at the first 5 rows of this new data set. Here we have 1 hot sex is male. We don't have 1 hot sex female because we dropped first. 1 hot smoker, yes. We don't have 1 hot smoker, no. And so that is what happens with the 1 hot encoder. And the reason why we could do that, drop the first one, is that when we say 1 hot sex male is 0, that means that person was a female person because this is 0. And this 1 means male. These are males here. 1 hot smoker, yes, that's a 1. The 0 says, oh, this person was not a smoker. Okay, so you can get a lot of the information that using the dropping the first column. The remainder, age, remainder, BMI, remainder, children, those are our numeric features is what I'm trying to say here. So let's split our data into training test sets with X train, X test, Y train, Y test, and this is equal to train test split. Here we have X encoded as our new X features with our Y, and we'll have a test size of, let's say 30%. That's going to be our holdout, is 30%. Our random state is going to be equal to, let's say 413. And this random state feature allows us to keep the same shuffle sample of data, so that if we want to perform this analysis on using a different algorithm to compare the errors to see which is better to use, this is great. Or if we want to change parameters to improve the model fit, and being able to work off the same selection of data provides consistent results. So this is why we have random state. We're going to instantiate our model. So we have model is equal to linear regression. Okay. Instantiate a model. The model fit, we're going to call it regr. Fit our x train and our y train. And now it's time to make some predictions. We're going to call predictions for the train data and the test data. So what we're doing here is we're projecting the charges using the training data, and what those charges predictions would be with this model that we created from the training data, and what the charges would be on that holdout test data set using the model that was created with X train and Y train. So for our Y prediction, we're going to have our regr dot predict X underscore train, and we'll do the same for the X test. This data here is going to, we're going to use, why is it highlighted? Oh, because we haven't run it yet. And so here we're going to use our R2 score, and we're going to get our R squared scores from the Y train and Y prediction. So this is going to be the comparison of Y train and Y prediction, and that calculation to give us our R squared score. Same thing for mean squared error. We're going to take the difference between our Y training and or actual Y values for the training data set and the predictive values from that training data, and compare to see how close they are. And so this is what these two are. And so here we see that we have an R squared score of 0.75. It's not bad. Compared to what we saw, if there was not very high linear correlation, it's not bad. I did do some other things with this to see that we can improve the model fit with actually a polynomial regression. Actually improve the model fit. So here we have our test. We have R squared score of 0.74. Not bad. And the training mean squared error, we would use these to do comparisons if we want to do follow-on or additional models to just compare. Hey, let's try polynomial regression as I mentioned, or try a different algorithm to see if you can get a better fit or a better outcome for our predictions. What you'll also notice that if you use a different seed, you may notice that your training set has it can actually be lower in this situation. K-fold cross validation could be one method that you can use, and we'll talk about that method in another video. But here, this is what we have today. And so if you use 413, you may get something that's similar to what I have here. All right, so let's take a look at the final results of the model. We're going to take the columns from our encoded data frame that we had before, and we're going to see what the regression coefficients are and what kind of impact the features have on the output, like which ones have the strongest impact. The largest impact on charges is whether or not a person is a smoker. Okay. All right, so that's it. Thank you for joining today. I hope that you enjoyed the video. You learned something from the lesson. If you did and you liked the video, give it a thumbs up, like, subscribe. It's great motivation to actually keep me making videos. Until next time, be well.